Morning, everyone. Right, so this is a project I've been working on for my master's degree over at UC Santa Barbara. And I'm just going to start with an example. So, say you're working with a local mix and you find that, because the song's melody spans several octaves, you need different settings throughout the song to make it sound the way you want across the entire vocal range. Current options we have today are, MIDI mapping in the digital audio workstation. You can control individual knobs with an external MIDI interface. But this, forces you to allocate hands or feet to update these parameters in real time. Performance environment, then this is very distracting. If you're working on a recording, you can always use automation, draw time-varying curve values by hand or using MIDI interface, but this is also pretty tedious. So the idea here was to see if we can automate some of these tasks while integrating with the existing music production tools. So in our example, say the effect parameter at play is the decay time, and the characteristic of the audio is the pitch. And in this example, there's this clear relationship between the content of the sound and the desired behavior of the effect. The signal-dependent behavior can be achieved by defining a control mapping from the relevant audio characteristics to the relevant effect parameters. So this work introduces an audio plugin designed to facilitate these control mappings in the DAW environment. I call it the Adaptive Digital Effects Processing Tool, or ADEPT. So let's hear how this sounds. You'll see the decay time knob changing according to the pitch. So ADEPT was designed to turn any plugin into an adaptive effect, where the choice of effect parameter and audio feature to drive the real-time adaptive processing is up to the user. And building this system within the DAW environment integrates it with existing workflows for music production and performance. But it also, the DAW is a rich source of these diverse, high-quality effects processing and synthesis algorithms, and kind of wanted to avoid reinventing the wheel. So it needs a feature extraction pipeline, a method for mapping audio features to desirable range of values for various target parameters, and a means of transmitting control messages to build a model of the DAW and the plugins within it, and to update the parameter values in real time. ADEPT builds this model of the DAW by sending queries and processing the corresponding responses to retrieve a list of all active all active plugins, their respective parameters, and the valid ranges of values for each parameter. It also sets up separate OSC connections to aggregate control data sent from all active instances of the ADEPT plugin. The control data is periodically forwarded to the DAW, which in turn updates the parameters, the values of the targeted parameters. So I used Juice as the core C++ framework for the project, Sencha for audio feature extraction, and a now somewhat outdated MIDI remote script called LiveOSC to communicate with Ableton Live. None of this would work without that remote control of the DAW. The automation and application state APIs are accessible
via these MIDI remote scripts, which are basically just Python libraries written for usually just specific control interfaces. But LiveOST is an open source MIDI remote script, which provides an OSC-based, open sound control-based interface for those APIs. Sure, many of you are aware of Essentia, but it implements a wide range of feature extraction algorithms, and using it, can easily expand the project to add more features down the road with more time. Now, critical to the design of this plugin was knowledge of the expected ranges of values for all those audio features, some of which vary significantly between different input audio signals. So my solution is to analyze a sample of the expected input signal in advance. This a priori information reveals the effective dynamic range of each audio feature for a particular performance, enabling feature normalization and the detection and elimination of outliers during real-time operation. The current approach to control mapping is simple. The user defines a range of input values within the detected limits for the audio feature, and a range of output values within the limits of the target parameter. Detected audio feature values falling within the input range are normalized, and these normalized values are simply denormalized into the user-specified output range for the target parameter. So let's take a look at the whole workflow, how we got to that example at the beginning. So this is our session. There's a reverb plugin on an auxiliary track and a vocal recording on a track with the ADEPT plugin. So first we're going to load that same recording and calibrate the plugin. We can visualize the extracted feature values to help correlate events in the music with changes in the audio features. So that's the dry recording. So we're going to be cranking up the reverb so we really see a dramatic effect here. But the next step is basically just to select the feature we want to use to map from and the parameter we want to use to map to. So here we can see all the different plugins in the session and their various parameters. We're going to use the decay time on the reverb. Now in the mapping interface, it's tried to go for some familiar controls. It's basically 2 sliders and a couple buttons and knobs. But this allows you to select the useful range of values for input and output, and to change the scale of those ranges from linear to logarithmic if necessary, which is helpful for something like pitch. We can also smooth the mapping output with a low-pass filter to avoid any sporadic jumps in the controls. We activate the plugin and can actually record its output with the automation arm.
In this strange land, do you feel lonely? Oh, how do you live? Show me soft skin.
So you can see it jumps right back down. I've got a few more examples here. This is a pretty simple one where you can get sort of a wah-wah sound using a bandpass filter on a guitar recording. So. this is just controlling the center frequency and the Q of that EQ band. Can do sort of an onset ducking delay effect. And an adaptive distortion where the detected dissonance will control the amount of drive with a couple of other controls mapped as well. And one more example here. So this is one that could be a little cooler using something like MFCCs to obtain some more peak frequencies. But in this example, I'm just using one, the detected pitch to control a resonant filter on the synthesizer. But the idea is to kind of give a vocoder-like effect, just using a few simple mappings.
Do you feel lonely in this strange land? Do you feel lonely? Oh, how do you live?
So I conducted a couple small pilot studies involving music production tasks to be performed with and without this plugin to collect feedback about the strengths and weaknesses of the design. Despite some bugs and limitations in the prototype, much of it was pretty encouraging, suggesting that something like this could be a useful extension of existing music production tools. Now, coming off of Brian's talk, this is definitely something aimed more at producers or people already familiar with the operation of all these effects. But I think, especially in terms of creative sound design, this is something that has a lot of potential, and as a prototype, it's a little bit limited, but you can imagine doing a lot more, especially if something like this was integrated more tightly with the DAW itself. I think this research and a lot of what we're doing here is pointing toward smarter DAW environments where this kind of feature extraction, routing, and especially semantic control, semantic interpretation, I guess, of this information, can really support adaptive processing for automated mixing, sound design, and have it all integrated as seamlessly as time stretching, crossfading, or automation is today. Right, so thanks for your time. That's pretty much all I've got.